So before we start, so I would like to explain that you will see some strange things in the format of the program. That actually is because we add 10 extra minutes to the half an hour or 40 minutes that at the beginning we said you will have to speak, just in order to give time for questions, discussions, and as well some time to relax from one talk to another. So there will be some talks that they will not be connected, so it's better to have time to erase everything in our memory and then try to forget everything and try to.
But tequila is better for that.
Tequila is better for that, but we cannot supply tequila during unfortunately. But for sure during the evenings we will have some interesting discussions with tequila and vodka. So I'm very glad to introduce Krzysztof, that I know everyone knows now. So, and he will speak about fractional Schrödinger operators. So thank you so much.
Thank you for the introduction. A very promising introduction. So this is about the joint work, which is now on archive. The title of the paper is updated. It says fractional Laplacian with the Hardy potential. The collaborators for this project are me, Tomasz Grzywny, Tomasz Jakubowski, and Dominika Pilarczyk. Can you hear me in the back of the? Okay, thank you. So this is just a few weeks ago that we finished the project. It lasts for about 3 years now. The plan is I would like to discuss how to get estimates for the hit kernel of this operator. Let me explain. Alpha is a number between 0 and 2. We are in RD. Kappa is a positive number less than kappa star. Kappa star I will explain in a moment. The fractional Laplacian sometimes is, or more often really, it's denoted in this way, which is more in agreement with the spectral theory of fractional powers of positive operators. And then now kappa star, I forgot d plus alpha here. So that's a number, and we want to have hit kernel estimate of P tilde being the hit kernel or transition density of this generator. So this is a Schrödinger type operator, a Schrödinger perturbation of the fractional Laplacian, and this is a perturbation which increases the mass of the semigroup. And if kappa is too large, the semigroup will explode. So this is critical in the sense that this is not a small perturbation. It cannot be resolved with usual methods. It requires methods that somehow respect the value of a constant. The biggest constant that we can have is kappa star, which is the best constant in some related Hardy type inequality, which I plan to talk about this in a moment. Let me give first some information about history. This is a classical topic for the Laplacian. For the Laplacian, there's a paper of 1984 by Goldstein and Barras. And they proved that with the constant large enough, so maybe let me state this equation. The equation for a function would be this is the appropriate counterpart in the classical setting. Kappa is supposed to be less than a critical constant, which then becomes d minus 2 over 2 squared. That's a kappa star in this case. And if kappa is less or equal to this constant, there exist positive solutions of such a parabolic equation, that is with a Cauchy problem for this operator, with positive initial values. If kappa is bigger than this d minus 2 over 2 squared, then no positive solution exists in the setting that they considered in this paper. So this was a very influential paper, which started a lot of research on that. Let me mention a few more papers. Vasquez and Zazua. That was 2000. In this paper, they emphasized the role of hard inequality. Another paper on this topic was Liskiewicz and Sobol. In 2003, and they gave the first estimates of the transition probability, transition density for this operator. Let me just for short denote it by p tilde. And this was only for kappa less than this critical Hardy constant. This was then improved by Millman and Semenov in 2004. To kappa equal to the critical constant. So P star was estimated in this case. I would like to talk about estimates of P tilde, and that's the main motivation. Millman and Semenov also gave some roadmap of how to approach such problems. And this roadmap depends on existence of sufficiently many superharmonic functions, so to say. There are other contributors, and obviously I cannot mention all. There was Italian school working on this. 2007, for instance, a paper which they studied the Dirichlet problem, boundary conditions, on bounded domains rather than on the whole of RD, which I had in mind in this discussion. Bounded domains are slightly easier for this problem, and this was already noticed by Vasquez and Zuazua. Namely, there are some superharmonic functions to use, and the Millman-Semenov method requires the lower boundedness of those by a constant, positive constant. And it's easy to have it on bounded domains, not on the whole of RD. That's basically the reason why the Dirichlet problem for this operator in bounded domains is a little bit easier, has a different flavor. Let me go to the fractional Laplacian. What is fractional Laplacian? It's some singular value integral. For instance, we can write it down this way. There's some constant. So that's a principal value integral of this type. In terms of Fourier symbols, this is similar to Laplacian, and it has symbol as in terms of Fourier transform. It also corresponds to It is a generator of Markovian semigroup, namely the semigroup of the rotationally invariant stable Lévy process with this alpha as we fixed between 0 and 2. So that's all well known. There's a stochastic process corresponding to this operator. So let me mention what analytic results exist for this problem of ours with this Hardy potential. Basically, there are two contributions, maybe three. So Frank, Lippenzai, Ringer. (2007, 2008). They have hit kernel estimates for a related by a different operator. There's some time change. So because of this time change, it's not obvious how to transfer this into estimates of our p tilde that we want for our operator. And there's a lot of work related to our problem and unrelated to our problem. I cannot discuss this in much detail. There is Abdelawi and Medina, Peral, and Primo. In 2016, and they have explosion if and only if kappa is greater than kappa star. I will explain what explosion is, but in simple words, it means that the hit kernel is infinite. We can make it precise. We can also talk about existence of positive parabolic functions solving this equation. And there is a recent paper on arXiv. Benamor. There are hit kernel estimates for this fractional Laplacian in bounded domains. So basically that's, to our understanding, the state of art in this setting. And let me say a few words how we approach this problem, from which angle. We study Schrödinger operators since almost 20 years. We started from probabilistic approach. We evolved more into analytic approach. Let me say about analytic approach first. We will talk about Schrödinger perturbations of transition densities or transition kernels. So we want the transition, let's say, density. Let's think about Markovian process, but it may be super Markovian object as well, on some abstract space. We want Chapman-Kolmogorov for all admissible arguments. And let us take a function that may be also a measure on X. This being given, we produce a Schrödinger perturbation of P. And it is defined as a series of, okay, let's call it Pn. P0 is P. It has 3 arguments. And then each next step is obtained by integration, composition of the previous one with Q. This is a composition space is limited here. Now that's P, T minus S, Z, Y. So that's basically a straightforward definition. This is also always well defined, but it may be infinite. Right? So the question is sometimes how to estimate it from above, because from below we always have P less than P tilde, less than that we don't know. It may be even the situation that this is infinite. And as far as probabilistic connection, here's one. Feynman-Katz formula. Consider a bridge. I want to use expectation for a bridge is joining 2 points in space-time, 0x and ty. 0 is time, x is space, t is time, y is space. And now this p tilde will be the original p times this expectation of a bridge, and we calculate expectation of exponential functional exponential of an additive functional, multiplicative functional of this form. I did not define x, but this is a process, Markovian process corresponding to p. Let's assume at this point that p is sub-Markovian, sub-probabilistic. Okay, so this is how we should understand this p tilde. This is interpreted as the total mass that the particle gets when moving in this potential q between time 0 and t. This total mass somehow multiplies the original mass. Here's a typical result that we obtained in the about 10 to 15 years ago, maybe 10 to 5 years ago, actually. A typical theorem. This is with a joint paper, in a joint paper with Tomasz Jakubowski and Sebastian Sydor. 2012. We want some bound on Q. A bound on Q should be done in terms of P, because there is some kind of interaction, a lot of interactions between P and Q visible in those multiple integrals. So one natural assumption is that the first integral, that is P1, is not too large. So the P1 is just this integral. So that's the usual Lebesgue measure on the line. This is some abstract measure space with the sigma finite measure dz. And now this is P. If now this is less than, that's the definition, if this is less than a small constant plus some function growing with time, Q, times the original transition density, then I will say a few words about this eta and Q in a moment. Then a similar estimate can be given for each Pn and also for P tilde. Let me just say for P tilde. I should actually use here. Most of our work is on, that's P1, yes. P1, yes. And there is no S. There's no S. Somehow we got used to time inhomogeneous, and this has actually the basic formulation for time inhomogeneous semigroups. That's T. So that's the definition of P1. If P1 is bounded in such a way, then P tilde, being the sum of all those Pn's, is bounded similarly times P1. And let me add some comments on eta and q. Here, eta should be less than 1. This means smallness. And q, this capital Q, should be superadditive. This should be positive this is positive function. Let me add for security. A typical function Q would be an integral of a positive weight. And if we have this integral bound, so this is a constant, this is some integral, then this integral bound transfers into P tilde. So this is good for many cases, but not for ours. One typical case would be for the fractional Laplacian, any constant times x to the power negative alpha plus epsilon. So anything with less singularity at the origin than negative alpha, we are quite good with that, especially then for the transition, the density of the fractional Laplacian, we have some other properties like 3G inequality and other estimates. So that's the easier case. Let me say a few words about the Hardy inequality. Now in our setting, there's a systematic method to construct a superharmonic functions for Markovian semigroups. And this may be quite useful, hopefully. I will say about the joint work paper with Dida and Kim, 2016. So let P be a symmetric transition density. Let f be an increasing function on half line. I want f of 0 to be 0, that's normalization. I want a measure on x. Again, this is pretty abstract. And let us define a superharmonic function. This will be an integral over ds, or dt is fine here, over the space. This with respect to the measure. There's the function, and there's the transition density. And the result is a function of x. Now, this may be finite or infinite, but if it's finite, then we have nice applications. Let me give an example. T to some positive power times the Gaussian kernel. I will, in a sense, I'm taking mu equal to Dirac delta in a D, and the beta is positive here, so that's F. The result is some constant explicit constant times x to the power 2 minus d, which is Newtonian kernel, plus 2 beta. Plus 2 beta. And here beta is somewhat restricted. So here's one example, and you get superharmonic functions. In which sense they are superharmonic? If you consider a semigroup given by integrating against pt, this semigroup on H is less than or equal to H. If H is finite, this is a, this is, okay, that's too early in the comment. There's too early a comment here. So let's also have another object of this type, an integral from 0 to infinity, f prime of t, pt, x, y. We need to integrate with respect to mu. And with respect, the example is finished. Now we get back to the general setting. And I want this setting. There's a similar integral of this type. F prime is positive because f was increasing. I want to divide this by h. And let this be a function q. Informally speaking, this is the generator of the semigroup acting on h, negative of it actually. You can call it the Riesz-charge of H, and we call it Fitzsimmons ratio. And this gives, it may give an interesting weight function here. For instance, for the Gaussian kernel, because as you differentiate the power function, you get the power function less, exponent less by 1. So the ratio will be here in this example a constant times x to the power negative 2. Which is precisely how we can study the Hardy type potential for the classical heat kernel. And by similar calculation, we can do it for the heat kernel of the fractional Laplacian. Now, let me make a connection to Schrödinger perturbations. The connection is as before. We take this Q as the potential. In the sense of those PNs. Oh, is it? I think we have. And here's a theorem from the paper with Kim and Dida. P tilde. First of all, I should say that as we define P tilde in this way, starting from transition density, let's say Q positive, we always get a transition density that is a semigroup, that is, it has Chapman-Kolmogorov. Now consider the semigroup on function h that we constructed, and this is less than or equal to h. This is a strengthening of this previous result, of this lemma, because P tilde is bigger than P as the integral kernel. This is also a finiteness result on P tilde, because we integrate it against something generally positive. We get something generally positive but finite. You need to work on your examples to give you such a statement. Okay, here's a complement of this, because I want to talk about Hardy inequality. Assume that this is subprobabilistic if we start from, as we start from P. That is submarkovian. If we assume this, we can consider quadratic form, defined as usual. That's the usual scalar product in L2 of this measure, reference measure dz. And then we will have u minus pt of u. It's known by spectral theory that this is well defined and monotone in T, and the limit exists for functions for which it is finite. Actually, it always exists, but we are interested in the domain of such functions for which this is finite. Here's the theorem. So remember, starting from f and measure mu, we constructed a superharmonic function in this sense, supermedian, if you will, in this sense. We produced Schrödinger perturbations, get some finiteness results. Let's forget for a while about the Schrödinger. Let's talk about quadratic forms. And here's a next consequence of this construction of H. The quadratic form is minorized, or is majorizes the function q times u squared dx. All u in L2. Provided if function u is equal to 0 on the set where h is equal to 0 or infinity. Sometimes we need to be careful, but it really, in those applications that we examined so far, it's not really a restriction. Those functions, like those power functions, have no problem except at 0, which is of 0 Lebesgue measure. So here's the estimate, and quite often we actually get equality, but I don't have time to discuss that. So we have H. H could be considered a ground state in some examples. By a ground state, let us, for this moment, understand a function which is invariant for a semigroup. So I want to go to this direction because, well, we have time limited. So getting back to the initial goal, I should say about Hardy inequality for the fractional Laplacian. The first person to mention is Herbst. There's this paper of Frank and Zeiringer in 2007. Beckner, 2012. And there's our paper with Dida and Kim. And in all those papers, I mean, for the results of those papers, we can take power functions and study either the Gaussian semigroup or the semigroup of the fractional Laplacian. And this produces functions H which are power functions. I just need to forget about delta. And if you want to think about f rather, if you want to think about f, it's a power function. Let's forget about the exponent. Let's talk about mu equal to Dirac delta, or just let's focus on power functions H with the superharmonic functions that we consider. So we want to think about potentials that are obtained from this Fitzsimmons ratio. Here's a certain description. For the fractional Laplacian, also for the Laplacian actually, if you take an exponent delta and consider the Fitzsimmons ratio, you get a constant kappa depending on delta and also on d and alpha, which is given by this graph. That's d minus alpha. I want to consider half of this midpoint of this interval. This is delta, this is kappa, this is the same kappa that we have here. We of course get this Hardy type potential as well. So the maximal value that we get here is kappa star, which we still have on the blackboard. This is the most that you can get. in this setting. Actually, you cannot improve hard inequality beyond this Q with kappa star. Here's a theorem whose main author was Tomasz Jakubowski, really, in the setting of the fractional Laplacian. So I just want you to focus on this setting only. Forget about the generalities. I want to improve this result. And here's the improvement due to Tomasz Jakubowski. That's serious work. Some kind of calculus that he devised. Here's a consequence. We want to understand the mass of this semigroup as well. And basically, here's a useful description. A mass plus h, well, h is easy in this now, but somehow mass is also bounded by this term. It's more compact form that I can give is this one. Pardon?
Does the constant depend on t?
No, constant does not depend on t. Yes, that's important. But it's not 1. It cannot be 1, really, because the mass is bigger than 1 of the semigroup. So the next theorem is this one. It's a factorization of approximate factorization of the semigroup for this operator. It uses implicitly function h, but let me forget about h at this moment. And there is the original p. The original p has no explicit estimates. Sorry, I did not discuss that at length, but let's assume this is kind of known. And here are the estimates good for all range of time and space. If kappa is less than kappa star. By delta, we mean here delta equal delta of kappa. That is the inverse function of the function that is here on the blackboard. I mean the inverse of this part of branch of the function.
Is there also an exponent on
Why?
There's an exponent on x.
Yes, thank you. The same one. It's symmetric semigroup. It's symmetric semigroup. Now, this is in a sense resolved, but we were stopped at this moment because we wanted to understand the connection of this to Davy's method. Davy's method is basically using Dup's conditioning to get estimates of a semigroup from on-diagonal estimates, and the on-diagonal estimates are obtained by Nash's method, basically. And I should be finishing. So we work for a long time, and the main contribution here comes from Tomasz Grzywny, who showed us how to actually be able to use Davis's method in this case. It was non-trivial, especially because the domain of the semigroup of P tilde was not explicitly described, not enough. So we have two methods back to back, the Davis's method and the method of basically using perturbation formula, which I did not discuss at length, and we kind of show an alternative to the Davis's method here. I need to stop here.
Questions or comments?
So in the classical Davis method is somewhat similar to these because you have to construct, so what you prove is the on-diagonal estimate, right? And then you construct this function which is super from that function. And then you make some choice, so you have to so are you able to do this estimate of the on-diagonal by some simpler method? If you just want to prove
We just use Sobolev type inequalities for on diagonal estimates. For this, let's say, conditional semigroup, we actually use the roadmap of Millman and Semenov, and so we don't really go into the much technique. What they need is that the superharmonic function is bounded from below, and now we have it here, basically. It's not really superharmonic because that's not a 1, but they want to have approximately superharmonic function bounded from below, and that's why it works now, thanks to this estimate. So the on-diagonal estimates we obtained by Sobolev inequality, especially in the kappa star case, the critical case that there was a certain problem because the existing Sobolev inequalities were restricted to the domain, which was the domain of the quadratic form of the fractional Laplacian. And the domain of the quadratic form of the Schrödinger semigroup for kappa equal to kappa star is bigger. That's the only case, the only kappa where the domain is bigger. And to somehow control this, Tomasz Bojdecki showed us how to do it, basically. That's kind of complicated function analysis, complicated for me, I would say.
Any other questions or comments?
Well, if this is not the case, then let's thank the